Here's answers to the free response from the Chapter 4 summative. The first set of questions all refer to students doing a series of experiments with a solution of copper chloride. First thing they got to do is make the copper chloride solution. So in this table, we're going to briefly list steps necessary to produce the 200 milliliters of aqueous copper chloride solution using the equipment given. All safety measures are already in place. Not all equipment or lines in the table may be used. And so we're just looking for kind of a general procedure. First, they would weigh the calculated mass of solid copper chloride. We'd use an electronic balance, weighing paper, a scoop. We use those plastic weigh boats, but weighing paper is kind of the same thing. Then, once I've got the measured solid, it goes in the 200 milliliter volumetric flask, not the beaker. Volumetric flasks are calibrated to make specific volumes of solution. But we don't know the kind of markings on this beaker. I don't know if it has just one line for 250 milliliters or if it's got markings every 50, 100 milliliters. I don't know. Beakers are good for reactions, but they're not good for making specific volumes of specific molar solutions. That's the volumetric flask. So the solid goes in the flask. You add a little bit of water, maybe like half the final volume. That 100 milliliters doesn't have to be measured precisely. I add some distilled water, swirl to dissolve. Then once my solid has dissolved, I add more distilled water until that exact 200 milliliters has been established. That's where maybe I would use the pipette too. I could use the little pipette to squeeze drops of distilled water until I get exactly 200 milliliters. Then I just swirl it one more time. I would not be like mixing things in the graduated cylinder. We could measure like the distilled water. Some people said like measure 100 milliliters of distilled water with the graduated cylinder, which is fine. You don't really have to measure the water precisely. Even that approximately 100 milliliters in step 3 is just enough to dissolve the solid. It doesn't have to be measured precisely. Other little boo-boos, often we'd say something about like making the solution in a beaker. No, we want the specific volumetric flask. Or sometimes we had people that would say, fill the volumetric flask with 200 milliliters of water, then add the solid. But I want the solid plus the water to be that exact 200 milliliters. So I want to dissolve the solid first in a little bit of water, then I'll go back and dilute to 200. Because if I start with exactly 200 milliliters of water, then dump in some solid, the solid's going to take up space, so my final volume will be too high. Part B. The student takes a 100 milliliter sample of the copper chloride and adds an excess of 1 molar sodium carbonate, causing the copper ion to precipitate as copper carbonate. Write the balanced net ionic equation. So I started with a formula equation. I have this copper chloride solution. It would be kind of a bluish green. I would add the colorless sodium carbonate. And all they're really showing me in the image is that I'm going to get a green precipitate of copper carbonate. They're not showing the other product because in the end, it's spectators. The other product would be sodium chloride, but the sodium is always aqueous, as well as the chlorine, unless it's with silver, mercury, or lead. So sodium and chlorine are my spectators. Make sure that you put the charges on the copper ion and the carbonate ion on the reactant side to show that they are aqueous ions in the solution. If you left the charges off, like just neutral Cu would mean copper metal. And obviously we don't mean for there to be copper metal formed. Part C went well. before the solutions were combined, a conductivity tester was placed in the original solution. As the sodium carbonate was added, the student graphed the change in electrical conductivity. I feel like we might have done that in the lab. The X should go on the point of lowest conductivity to represent the stoichiometric ratio. Now it's not like zero conductivity because there are spectator ions. The sodium and the chlorine are still in solution. But at the point of lowest conductivity, I have removed as much copper and carbonate ion as I possibly can. Those ions have formed a precipitate. They have been removed from the solution. The conductivity should be at its lowest. When the conductivity is going up at the end, now I've added excess sodium carbonate. So the sodium and the carbonate ions are all going to show an increase in conductivity. All right, then part D. All right, here's another particle model question. And my brain just thinks groups. Whenever I see these particle model questions, I want to group particles together so that on a small scale I can figure out like what ratio I have. I can look at the balanced equation, like what ratio should I have. And so I've got a diagram that gives an incomplete particle representation of the reaction. The beaker on the left shows the initial mixture of reactants. I want to complete the diagram on the right. Be sure to include, number one, the correct type and number of particles based on the number shown in the original solution. And number two, the relative spacing to depict the appropriate phases. So are these particles going to be solids? Are they going to be in solution, aqueous, ions? And then like where should they be? Solids would sink to the bottom. Ions would remain floating around in the solution. Okay, so I looked at the balanced equation and said every time I can find 3 plus 2 copper ions, they would react with 2 of the solid aluminum atoms. So I grouped it together and then said anytime I can group that ratio of reactants, I should form 3 solid copper atoms and 2 aluminum plus 3 ions. I was able to do that twice. So I could circle the 2 aluminum solid and the 3 copper plus 2 ions and make 3 more solid copper and 2 more aqueous aluminum plus 3 ions. Okay, so that gives me then on the product side a total of 6 solid copper. So I got the 6 copper down toward the bottom of the beaker. That's where the solid would go. And then I've got a total of 4 aluminum plus 3 ion. So I've got those kind of separated up on the top. They're floating around in the solution. Well, then I've also got some particles on the left that never reacted. It's kind of an interesting reaction with the ratio being kind of funky. You've got both excess aluminum and excess copper ion. There's 2 solid aluminum that were not reacted, and they kind of showed those in the beaker on the right. But there's also 2 plus 2 copper ions that never reacted. So they would also still be swimming around in the solution. So I should have a total of 6 copper down at the bottom, solid, 2 copper ion remaining aqueous. Then I've got 4 aluminum ions in the solution, and then the 2 aluminum that were also unreacted solids. Oh, I like that one. Then the second free response was my solution stoichiometry. There were a couple versions. So you've got this one, or maybe your numbers are a little bit different, but then you got another one to look at as practice. I'm mixing a solid sample of lead nitrate with some sodium iodide solution. The key is that I might start with solid sodium nitrate, but all nitrates are aqueous, So when I mix that with the aqueous sodium iodide solution, there is water present. So in the balanced equation, they're showing the lead nitrate as aqueous because it will dissolve in the sodium iodide solution. First thing I want to do is calculate moles of each reactant. So I have the 1.5 grams of solid lead nitrate. I can just switch grams to moles. And then I've got, 0.1 molar solution of sodium iodide, 0.125 liters. So I'm going to cross multiply to get moles. Please show your work. Obviously, you have to show your work on the AP test, even though this is really simple. If you just have a simple calculator error and you show no work, you get nothing. Or if all you do is show the right answer, but with no work, you also get nothing. So it's to your advantage to show work. Sometimes people were kind of just making bonehead mistakes on the molar mass of lead nitrate. And if you had it all set up, I could tell that you meant to do the right thing. You knew how to switch grams to moles. Yes, maybe you got the wrong mass on your calculator. But if you had nothing shown, I can't give you anything. B is the limiting reactant. So I look at my balanced equation. I'm supposed to have twice as much sodium iodide. And I actually have a little bit excess. Now you could show the work. I actually plugged it in my calculator just to check. I knew it would be a little bit close. 0.009-ish moles of sodium iodide needed. I've got a little bit extra. So that means the lead nitrate is my limiting. In part C, we'll use the limiting to determine the mass of precipitate formed. So I've got moles of my limiting reactant, lead nitrate. It's a 1-to-1 ratio in the balanced equation. And then I can multiply by the mass of lead iodide. Sometimes people picked the wrong limiting reactant. But here in part C, they had all their work shown. They had units shown in their work. So again, sometimes if it's just numbers, but they're chicken scratches and nothing looks like organized stoichiometry, in that case, you'd probably get nothing. It's not the grader's job to pull out their calculator and try to figure out your logic. They're not trying to jump into your head and figure out what was this kid thinking. If it's not clear where your error would fall, then you get nothing. But in a few cases where somebody picked the wrong limiting reactant, but they did the stoichiometry correct, they still got the point in part C. And then D, when the reaction is complete, what ion in solution will be present in the greatest concentration? Calculate the molarity of this ion. Well, it's probably one of the spectators, right? So it's probably either the nitrate or the iodine. So you got to just kind of check. I took moles of what I had, moles of lead nitrate, moles of sodium iodide from part A, and then said, okay, well, there's 2 nitrate ions per unit of lead nitrate. So multiply that by 2 to get the amount of nitrate ion. There's only 1 sodium ion per sodium iodide, which actually ends up being the winner. 0.0125 moles of sodium just edges the 0.009-ish moles of nitrate to be the ion in highest concentration. Then to find the molarity, I would just divide by the final volume, which here we had a solid in a solution. Sometimes if I had 2 solutions, that final volume right here would be the combined volume of the 2 solutions. But here it says that it's just a solid being added to the 125 milliliters of sodium iodide. Assume there is no change in volume when the solid is added. So then the final volume can stay 0.125 liters. And then E again, particle models, I love it. Circle the diagram that best represents the results after the solutions have been mixed. Explain the reasoning used in making your choice. Note, the sample of ions shown may not represent the exact like stoichiometric ratios. So we're really just kind of qualitatively looking for the model that, number one, shows the correct precipitate. So that should be the lead iodide. And then number two shows the proper ions that would remain in solution. So it's got to be my spectators, the sodium and the nitrate. And then it's also the ion in excess, where most turns into a precipitate, but there would be some left over. And that'll be the iodine. Most is in the precipitate, but it was also part of the excess. Now the second version of this question was really similar, just some different numbers. So it's a great practice if you didn't get the original version. Here's the other option. 5.2 grams of lead nitrate, turn it into moles. 0.1 molar sodium iodide, 425 milliliters, or 0.425 liters. I've got moles of each reactant. I want to figure out the limiting reactant using that 1:2 ratio in the balanced equation. I calculated that I would need a little over 0.03 moles of sodium iodide, and I have a little more than 0.04 moles. So again, we've got excess sodium iodide. The lead nitrate is limiting. We use the limiting reactant to calculate, there it is, mass of precipitate formed. Starting with moles, why not? You already have it in moles. You can go to the ratio in the balanced equation right away. It's 1:1, and then I multiply by the mass of the lead iodide. Part B then is also very similar. So I'm looking at the two spectators as my choices for ions of greatest concentration remaining in the solution. Then I just got to check to see, all right, which one is the greatest. So there's 2 nitrate ions per unit of lead nitrate, which gives me about 0.03-ish moles of nitrate. But the sodium is still the winner. 0.0425 moles of sodium. And again, no change in volume when we add the solid to the original solution, so the final volume is 0.425 liters. And then again, the last part would have been the same. I want to choose the model that has the right precipitate. The sodium and nitrate spectators are still in the solution, and there should be excess iodine. The lead is gone. There should be no lead ion remaining in the solution. It's in the precipitate, and it's also part of the limiting reactant.